St. Joseph College for Women, Autonomous Vishakhapatnam. Welcome to St. Joseph Open Web-based learning platform, So E-Learn, for a soulful and enriching e-learning experience. Department of Chemistry presents St. Joseph's massive open online course, Solid States. Contents 3.8 Bragg's Law and its derivation, 3.9 Defects in crystals, 3.10 Schottky and Frankel defects. 3.9 Bragg's equation. W. Henry and W. L. Braggs, father and son, formulated the study and studied the concept that each crystal plane reflects radiation like a mirror. They analyzed scenario of both constructive as well as destructive interference. When a beam of X-rays pass through a crystal, each atom along the path acts as a scattering center, resulting in the emission of radiation. William Henry, his father, and William Lawrence Bragg, his son, both got Nobel Prize in the year 1950 for the secondary radiation. Bragg's law is a special case of Liouville diffraction which determines the angles of coherent and incoherent scattering from a crystal lattice. Coherent scattering is the phase relationship between the scattering waves that is maintained. In this case, the waves remain in their original alignment. The scattered wave can interfere with each other, that is either with constructive or destructive. In incoherent scattering, the phase relationship is lost. Each scattered wave moves in random direction. There is no interference pattern. The overall effect is like random diffusion of light. Coherent scattering, the scattered light waves stays as the same as original. They can interfere, that means they can add or cancel with each other. They also have the capacity to form as pattern and colors or rings. Incoherent scattering, the scattered light waves are not in steps, that means they are disturbed randomly. They do not interfere, so no pattern is formed. When light hits a molecule, most of it is scattered without any change in energy. This is called as Rayleigh scattering. The wavelength or frequency that remains same. The scattered light appears at the same position in the spectrum of the original light. In Raman spectroscopy, the Rayleigh line is a strong central peak. It is not shifted and it is taken as a reference point. Other peaks are obtained. They are called as Stokes and anti-Stokes lines. They are obtained due to energy differences. 3.8 Derivation of Bragg's law. Consider the following figure of beams in which the phases of the beams coincide with the incident angle which is equal to the reflecting angle. Here the incident beam are parallel to each other until they reach the point Z. When they are at point Z, they strike the surface and travel upward. At point B, the second beam scatters. AB plus BC is the distance that is travelled by the second beam. That means the second line. The extra distance is known as integral multiple of wavelength, which is represented by d, small d. The X-rays diffracted from an atom in the plane of a crystal that obeys the laws of reflection. The two rays reflected by successive planes will be in the same phase. The extra distance traveled by the second ray or the line is an integral number of wavelength. Here, the extra distance in the bottom line is called as path difference and it is equals to n lambda. Here, half of the distance is traveled by the incident light and another half is traveled by scattered light. Let path difference is given denoted by n lambda and which is equals to AB plus BC. Let us consider triangle ZAB. According to trigonometric function, sin theta is given by opposite side by hypotenuse. In triangle ZAB, opposite sine is equals to AB and hypotenuse is equals to ZB. Therefore, sin theta is equals to AB by ZB. AB, therefore AB is equals to sin theta into ZB. Here ZB is equals to D. Therefore, AB is equals to sin theta into D. Similarly, in triangle ZCB, the trigonometric ratio sin theta is again given by opposite side by hypotenuse. Therefore, in triangle ZCB, opposite side is represented by BC and hypotenuse is represented by ZB. Therefore, sin theta is equals to BC divided by ZB. Therefore, BC is equals to sin theta into ZB, where ZB is equals to D. Therefore, the value of BC is equals to sin theta into D. Let us assume that AB is equal to sin theta into D is equation 1 and BC is equals to sin theta into D. We know that AB plus BC is equals to n lambda, which is equals to the path difference. Let us represent this as equation 3. From equation 1 and equation 2, the values of equation 1 and equation 2 are substituted in equation 3. On substituting, we get equation 3 as n lambda is equals to sin theta into D plus sin theta into D. Therefore, n lambda is equals to 2D sin theta. This is called as Bragg's equation. Here, n is order of reflection, which is an integer and its values are 1, 2 and 3. Lambda, it is the wavelength of the X-rays. D is the distance between the two atomic layers. Theta, it is the angle between the X-rays and the atomic layer. 3.9 Defects in crystal. The basic classes of crystal defects are point defects, which are also called as zero-dimensional defects, line defects, which are also called as one-dimensional defects, surface defects are also called as two-dimensional defects, and volume defects called as three-dimensional defects. The point defects are one-dimensional defects when an atom is missing or an atom is in an irregular place in the lattice structure. The corresponding defects are known as point defects. The point defect produces strain in a small volume or the crystal surrounding the crystal but does not affect the perfection distance parts of the crystal. Generally, point defects occurs in metallic and ionic crystals. Point defects are of four types. They are vacancies, interstitial defects, substitutional defects, and electronic defects. Vacancies are simplest point defects in a crystal which refers to a missing atom in its site. The defect due to the missing atom of the lattice sites are called as vacancies. Here in the figure we can see the missing atom at their lattice site. Vacancy defects are mainly due to the imperfect packing during the formation of crystals or due to thermal vibrations of atoms at high temperatures. At high temperatures, atoms are frequently and regularly changing their position, leaving empty lattice sites behind their position. The number of vacancies per unit volume of the crystal depends upon temperature. In most cases, diffusion can only occur because of vacancies. In case of ionic crystals, there are two types of point defects that are related to vacancies. One is Schottky defect, the other one is Frankel defect. 3.9 Schottky defect. It is a special case of vacancy defect in ionic crystals. When a pair of vacancies is produced at one positive ion site and one negative ion site due to absence of positive and negative ions, then this type of defect is called as Schottky defect. In ionic crystals, there are two types of possible vacancies, namely cationic vacancy and anionic vacancy. That means the Schottky defect can be caused due to the vacancy in anion or a cation. When a positive ion from the interior of the lattice moves out of the crystal to its surface, then the positive valency is formed at its site. The formation of positive ion vacancy results in excess negative charge inside the crystal. To maintain charge neutrally, a negative ion moves to the crystal surface, creating negative ion vacancy at its site. Schottky defect may occur when positively charged ions and negatively charged ions leave their lattice site, creating vacancies. In a crystal structure, they reduces density of the. Let us take an example of NaCl crystal. Here Na plus is a cation and Cl minus is anion. The Na plus and Cl minus ions are arranged in regular lattice. Each Na plus is surrounded by Cl minus ions and vice versa. If one Na plus ion and one Cl minus ion leave their respective lattice position, they may move to the surface of the crystal to get lost to the environment. This create vacancies or empty spots in the structure. These vacancies are side by side. Therefore, it is also called a Schottky defect. Schottky defect results decrease in density and the crystal becomes slightly less stable, but it remains electrically neutral. It has high temperature. 3.9 Frankel defect. It is a special case of vacancy and interstitial defects in ionic crystal. When a pair of vacancies is produced at one positive ion site and one negative ion site by replacing positive and negative ions, then this type of defect is called as Frankel defect. Consider the periodic distribution of positive and negative ions in an ionic crystal. When a positive ion leaves its site and settles in the interstitial position, then it creates a vacancy in its position. Thus, a vacancy and interstitial defects are created. This pair of defects is known as Frankel defect. In case of Frankel defect, charge neutrality is maintained. Frankel defect occurs when a small ion leaves its normal lattice site and moves to its interstitial site. A cation vacancy at its original site, an interstitial cation at the new position. Let us take an example of AgCl for the formation of Frankel defect to describe the following figure. In AgCl, the Ag plus ion is much smaller than Cl minus ion. The Ag ions leave its normal lattice site and it moves into the interstitial position. This creates a vacancy where Ag plus was originally located. An Ag plus interstitial defect in a space within the lattice is created. The Frankel defect occurs in AgCl because the cation Ag plus is small enough to fit into the interstitial space. The crystal maintains electrically neutrality because no charge is added or removed. Thank you for listening to my presentation.